Hey everyone, today we're analyzing an overhanging rolled steel beam with these specifications over here. It's supporting a point load P of 700 kilonewton at the free end. So let's list our given values and pull the geometric properties. From the standard steel tables, we will find all of these values. Our load is 700 kilonewtons, our A is 2.5, and our allowable normal stress is 100 megapascal. Now what we're gonna do is draw a free body diagram that looks kind of like this. And we're gonna label our forces that are acting on this free body diagram. So we have our reaction A, then we have our reaction at B, and we also have our load P. Everything is A apart. And then let's draw one more free body diagram. This time we're slicing it right here. So that just means that we're gonna have a reaction at B. I mean, this is kind of confusing, but basically it starts right here. Like we cut it in half. When we do cut it, that means that we have a moment now and also a shear stress, V. Again, this is A apart. Okay, now that we drew our free body diagram, we can do the sum of the moments at point A. Let me just transfer this. So if we take the sum of the moments at point A, anti-clockwise positive, we get that RB times the distance, which is A, minus our load P, which is 2 times A, equals 0, 1,400 kilonewtons. Then we can take the sum of the forces in the y-axis. Let's take positive for upwards. That will give us the reaction at B minus the reaction at A minus P equals 0. That will give us reaction at A equals to 1,400 minus 700, which equals to 700 kilonewtons. So we found the reaction at A, which is also equal to the shear stress. So 700 kilonewtons. If we take the sum of moments clockwise, over here means negative M. And since reaction at A is anti-clockwise, that means that it's a positive moment. So reaction at A times A equals 0. That means that our M equals to 700 times 10 to the power of 3 times 2.5, which equals to 1.75 times 10 to the power of 6 nanometers. So now to find the absolute maximum normal stress in the beam, we use the elastic flexure formula written in terms of the section modulus, because this directly relates the peak internal bending moment to the worst case stress experienced at the absolute outermost fibers of the cross section. So this is the formula over here, and we plug in what we just found. The section modulus is given to us from the tables are written over here, and if we do the calculation, we get 94.59 megapascals. Moving on to part B, the problem asks for the maximum principal stress, specifically at the junction of the flange and the web. This is a critical region because it experiences a dangerous combination of both bending stress and high shear stress. First, let's find the exact vertical location of the junction, which we'll call YB. We find it by taking the distance of the outer edge, C, and subtracting the thickness of the flange. Both are given from the tables, and we get the result of 430.8 millimeters. Next, we use a linear proportion to find a normal bending stress acting right at the specific height, since bending stress decreases linearly from the outer fiber to the neutral axis. This is the equation, and we plug in what we found, and we get an 86.06 megapascal. Now we need the shear stress at the same junction. We use the shear formula where we need the first moment of area for the flange section above the junction. So to find the centroid of that isolated flange area, YF, we use this equation and we get 452.15 millimeters. And the area of the flange is given by this equation, which is basically width plus thickness. Both are given to us from the tables. And then our first moment of area is given by area times YF. And we calculate this and get 8.186 times 10 to the power of 6. Now we substitute everything into our shear formula to find the matching shear stress at the junction over here. Now that we have both the normal stress and the shear stress acting at the junction, we use the shear transformation equations to combine them into the maximum principal stress. We first find the average stress component, which is 43.03 megapascals, and then we find our radius. And finally, adding the radius to our average stress gives us the maximum principal stress at the junction, which is 93.93 megapascals. Finally, for part C, we need to check if this W920 by 449 shape is acceptable. We do this by comparing our calculated maximum values against our structural limit, which is the allowable normal stress. In this case, it's 100 megapascals. Since both of them are less than 100 megapascals, this beam is acceptable. Thank you for watching, and I'll see you in the next analysis video.